And another stoichiometry problem, now working with pyrite.
Binnacle project.
Let's read together the statement. It says that the roasting of pyrite occurs in the presence of oxygen, producing iron 3 oxide and sulfur dioxide as products. So the first thing we're going to do is to write the chemical equation. That is pyrite reacting with oxygen gas in order to form iron 3 oxide and sulfur dioxide. And it's time to balance the equation. Here you can see the oxygen alone, so let's leave it for last. One iron atom on the left, but 2 on the right. So by placing here number 2, we have already the iron atoms balanced. 2 times 2 is 4. So let's place here number 4 in order to have already the sulfur atoms balanced. And here, oxygens, 3 plus 4 times 2, 8. 3 plus 8 is 11 oxygen atoms on the right. So how can we get here 11 oxygen atoms also? Let's write 11 halves. With this number, we are canceling the effects of this other. So we have already 11 oxygen atoms on the left. But if you consider improper to work with this denominator, you can multiply all the equation by 2. And thus we have 2 times 2, 4 of pyrite, plus 2 times 11 halves is 11 oxygen atoms, 2 times iron 3 oxide, and 2 times 4, 8 of sulfur dioxide. And this is the equation we are working with. And now let's read together section A in order to know what they are giving us and what they are asking us to calculate. It says, how many kilograms of iron 3 oxide, they are asking to calculate kilograms of this substance, will be obtained by processing half a ton of pyrite. This is half a ton of pyrite, which means 500 kilograms. With an 80% FeS₂ purity by mass. The 80% of this stone is FeS₂. And we are calculating the kilograms of this substance in order to inject properly our conversion factors to move to iron 3 oxide. So let's calculate the 80% of 500. That is 80 divided by 100, multiplying 500. And here we have 8 times 5, 400 kilograms of FeS₂. And now it's time to bring our conversion factors. So let's do it. 400 kilograms of FeS₂, and our first conversion factor will help us to move from kilograms of FeS₂ to get into grams of FeS₂. Don't forget that it is very necessary to have this data in grams. And as you know, 1 kilogram is 1000 grams. The next conversion factor will help us to move from grams of this substance to move into moles of this substance, okay? And only with 1 mole we will have this conversion factor done. And now it's time to add the atomic masses. You know, iron 55.8 plus 2 sulfur atoms, that is 2 times 32. We are using our calculator, and 55.8 plus 2 times 34. This is 119.8 grams of this substance, okay, pyrite. The next one will help us to move from moles of pyrite to get into moles of iron 3 oxide. iron 3 oxide. And there comes the stoichiometric coefficients, that is 4 for this one and 2 for the other one. Okay, now we are moving in iron 3 oxide. And our last conversion factor will help us to move from moles of iron 3 oxide to present the result in the form of grams of this substance. Okay? With 1 mole, as always, we will have done this conversion factor. And now it's time to add the atomic masses, that is 2 iron atoms, so 2 times 55.8, plus 3 oxygen atoms, and that is 3 times 16. Let's do 2 times 55.8 plus 3 times 16. And we have 159.6 grams of iron 3 oxide. And now we are doing with our calculator 400 plus 1000 multiplying 2 and divided by 119.8 times 4. And we are obtaining 1669.4 grams of iron 3 oxide. But as we are asked to express the result in the form of kilograms, this is 1.6694 kilograms of iron 3 oxide. Easy, right?
Binnacle Project.
And finally, let's read together section B, which says, what volume of air measured at standard temperature and pressure, that is 273 kelvins of temperature and pressure 1 atmosphere. Okay, these are the conditions. What volume of air measured at standard temperature and pressure is needed to process this amount of pyrite, if the air contains 21% oxygen by volume? Well, what are we going to do? As you probably know, we are using this formula. Pressure multiplying volume equals number of moles, number of oxygen moles, multiplying the Rydberg constant and temperature. So we need moles of oxygen, and we are moving using our conversion factors. We are moving from this 400 kilograms of pyrite into moles of oxygen. Moles of oxygen, not grams, only moles. So 400 kilograms of pyrite. The first thing we're gonna do is to change from kilograms into grams. And as you know, 1 kilogram of pyrite is 1000 grams of pyrite. Okay? The second conversion factor will help us to move from grams of pyrite into moles of pyrite. Only with 1 mole we will be doing our conversion factor. And let me use the calculator to add the atomic masses. Iron 55.8 plus 2 multiplying 32. And we obtain 119.8 grams of iron of pyrite. Now it's time to change from moles of pyrite to get into moles of oxygen. And there comes the stoichiometric coefficients, 4 to 11. And we are doing with our calculator 400 multiplying 1000 plus 11 divided by 119.8 multiplying 4. And we will obtain 9,182 moles of oxygen. And now it's time to calculate the volume of oxygen that we need. That is pressure, 1 atmosphere. The volume is what we are asked to calculate. Number of moles of oxygen, 9,182 moles, multiplying 0.082, the Rydberg constant, as you can read from the statement, and temperature, 273, and the result will be 0.082 multiplying 273, we are obtaining 205,547 liters of oxygen. These are the liters of oxygen gas that we need. This is the volume of oxygen that we need to roast our 400 kilograms of pyrite. And we are asked to calculate the volume of air, not the volume of oxygen, but the volume of air. And it says that air contains 21% oxygen. Look, imagine that this is our room with air. This is air, okay? And it says that the 21% of this room is oxygen. So, as you can see from this sketch, you can see that the volume of air must be greater than the volume of oxygen. The volume of air must be greater than the volume of oxygen. So, how should we place this data of the 21%? On this way? Multiplying by 0.21, or this other one? One of these calculus will give us a greater amount of air than oxygen. And you can use your calculator and you will see that this is the correct way to obtain the volume of air in order to be greater than the volume of oxygen. So let's use our calculator to do 205,547 divided by 0.21, and we are obtaining 978,795 liters of air. This is the solution for B section.
Binnacle project.
Well, it's been a little harder, right? But consider that you already have every tools you need to solve any stoichiometry problem. It's just a question of reading slowly the statement in order to know what they are giving us and knowing what they are asking us to calculate. But you must feel very proud of being here. For my part, it's been a pleasure to help you with this standard. So, congratulations. And now, watch a theory video if you think you've gotten lost in some aspects, or skip to the next exercise to continue climbing. And as always, like, turn on notifications and comment. See you soon!